Okay, the recording is on now, right? Yeah. Okay. I have one announcement to make. Uh, the exam is, of course, on Wednesday. It starts at 6 o'clock in the evening. You better be live 10 minutes before in Baskerville 210 in order to sign in. And then the exam will pop up on the blackboard from 6 to 8:15 p.m. I think I will allow for a couple of minutes for you to, you know, click and save and so on. And the number of questions, I have finally decided. I haven't exactly decided the actual, but it may be 22 questions instead of 27, so that you get at least 6 minutes, if not a little bit more, per question to relieve the pressure on you. All right, because test one, test two, test three is all in 5 minutes, 5 minutes, 5 minutes, and then I know there are some who really, let me say it again, I will not, as per original intention, give you 5 minutes per question, and since there are 135, is it how many minutes? 2 hours, 50, 135. Therefore, it is 20, is it 27 questions. I will instead give you 22. I have not finalized the final. I'm still trying to make it, how shall I say it? Make it such that you, as a biomedical profession, can at least say, I know something about the general physics. I know what are going to be more and more relevant in my biomedical profession. So I know about electricity. I know about this magnetism and the subtlety of magnetism. And I know about light. I know about all the various lenses that I need to use, the mirrors that I need to use. And I also know something about this, some guy called Albert Einstein, there's this thing, who has now given us this picture of photons. And there's a lot of, photons all around. Even right now, they are interacting with you and me, because without photons, I cannot see. And so we will want to be able to say that you, as having taken this course in general physics for biology students, that you can then be one of the healthcare workers, be one of the people in the biomedical profession, whether it is in making new prosthetic devices or even in coming up with a new vaccine. And I just want to say at this point to remind people, City College is proud to have Salk. The Salk vaccine was invented by someone who is a graduate of City College, CCNY. So be a good worker, frontline worker, and think outside the box, but be aware of what is the rule of your field within the box. You want to think outside the box, you want to be sure that you already know what is inside the box. And what's inside the box are the things that have been established about how things work in our world. All right. So the main big announcement is that I will not put 27 questions. I will put 22 or maybe 20, I don't know. But 22, I would say for sure, no more than 22 questions, so that you have at least 6 minutes per question. And so my advice is, whatever is the question at hand, all right, whatever is the question at hand, don't immediately say, oh, I have only 5 minutes. Gee, I must immediately, boom, boom. You plunge into it, and then you will most likely, probably, high probability of failing. I mean, in that question. All right. So what you need to do is to now say, gee, what happened? Was there to now say, I got a little bit more time. I will now read this question carefully. And I will read it because the wording sometimes is a little bit tricky. I mean, you do have to, because real life situation also, you have to be a little bit aware of what you're talking about. And to then say, what is this question asking for? Well, if you think it is, let's say, I don't know, Coulomb's law, or I don't know, who is this Faraday or whatever. If you say, oh, it has something to do with that, then you now go to whatever notes you have, and since you have your laptop with you, you can have access to all of the notes on your laptop. Then you'll be able to say, oh, maybe what I need is this equation, and then be careful of the units. When you apply the equation, be careful of the units, because after all, sometimes it can be in centimeters instead of meters. Sometimes it can be, I don't know what other silly units these people use. Well, you have to be careful of the units and then apply the formula in the right units for whatever the question was. All right. So the main thing is take your time, and the there will there's that's what's that sound? Is that, do you hear that sound?
Was someone raising their hand?
Oh, okay. Then what was the question? Raise your hand.
Oh yeah, Professor, I had a question. For the first two exams, at the end
Mm-hmm.
of the first attempt, we could see which one we got right and which one we got wrong. And then going into the second attempt, we could just do whatever we did for the first attempt for the right questions, and then change the ones we got wrong. But for the third exam, I noticed that we didn't have that anymore. Will we have that for the final? Will we be able to see which one we got right in the first attempt?
You mean before you get on to the next question, you then say, hey, did I get it right? Is that what you mean? That the blackboard let you have that?
Oh no, like and when we finish the first attempt, when we finish
Yeah,
answering all the questions in the first and
yeah.
second exam, we could see which one we got right. It would say like 5 points out of 5 points. And the one we got wrong, we saw 0. And then we do the
You mean,
second attempt.
right. Oh, I see. Between the first attempt and the second attempt, you already could see?
Yes, for the first and second exam, but for the third one, it didn't show at all.
I don't know. I have to look into, because Blackboard is so very complicated in the way of, even in setting, there were so many little dots here to dot there. But I I have to think about whether that is good or bad. Maybe
Okay,
it's good. I don't. Maybe that's good. I don't know. I have to look at it. All right. Thank you for
okay,
letting me.
okay, thank you,
Letting me.
Professor.
Okay. All right. Any other? Was there another hand raised? Okay. If not, let's go on. What was it I said? Yeah. I just want to encourage you that be a H Salk in, when you graduate, go for a career and be ready to think outside the box. Now, what was that? The chat or some question? Somebody had a question. Yes, you had a question?
Oh, someone was just asking if all the three exam grades were updated.
Oh, yeah, yeah, yeah. No, no, I have in my spreadsheet, I have updated all of them. Okay. All right. So now today we want to finish off reviewing light. chapter 26 and 27, and yeah. So here we now just quickly go through. You already know it, that we have this issue, or we know that light is a electromagnetic wave, and it really is zipping through space. Vacuum. You don't need any medium. You don't need air. You don't need water. It just flies across from the sun to us at a very high speed, 3 times 10 to the 8 meters per second. And but when it comes to the air, when it comes to the water, oh, it begins to slow down. And then you can say, how or why? That's because electromagnetic wave is electric and magnetic field, and it is oscillating in sync, right? But when it comes near the oxygen, nitrogen, ozone, carbon dioxide, oh, the electric field now affects the atoms, the electrons and the nucleus. And so then, because of this interaction, now the speed of this electromagnetic wave is slower. Because after all, it is basically like photons are crashing against your nucleus. And so they are losing their momentum. So they are losing their speed. So in the medium, in a material, the speed of light is less. And it is less by this index. And this index is always greater than 1 because it will always be slower now, right? Because the speed in the medium is slower, therefore this index is always greater than 1. All right, so you can say, how much greater? That leave it to the experts. We are not going to say, I must remember it is 1.3, 1.5. It does not matter. It will be given to you for water, for glass. And then there's this very important Snell's law, which you already remember. I don't know his first name, but the Snell's law says that whatever is the index of refraction in the first medium and the index of refraction in the second medium, then the angle of incidence relative to the normal versus the angle of refraction, because the refracted ray will now come out. And the refracted ray in the denser medium is always now closer to the normal, bent closer to normal. And the best way to remember Snell's law is to write it as n1 sine theta 1 equal to n2 sine theta 2. All right, so this is now the fundamental formula for all of the issues involving refraction and okay. And whether you do it over here or down here, well, you just have to remember that if it is coming from down here, when it comes up, it will now be bent away from the normal, right? So you can use applications, then we have already done that. It's I am taking from the earlier slides from the lectures that we have. So these are just simple calculations. We're not going to spend any time with it. But what is important is that then it is this Snell's law that enables us to now actually figure out many things. If you are looking for the sunken treasure and you are on the boat, when you look, if you indeed found a sunken treasure, the apparent depth of this treasure is less than the actual depth. The actual depth is here, but when you now look at it, it appears to come from somewhere here. So this is therefore the apparent depth, and you already can work out the apparent depth. You can work it out. This is just trigonometry. Once you know it involves Snell's law, the rest is algebra and trigonometry, and here you have it. I mean, you have already done that in our lessons before, so I'm just quickly going over review what I want to emphasize. And now, one thing, if you have, let's say, a swimmer underwater and looking up at the surface, someone holds a coin in the air directly above the swimmer's eye. Does the coin appear to be higher or lower. Let's say he holds a coin and you are now looking at the bottom. The coin would appear to be higher or lower. Well, if you see this diagram, you can then say immediately that the apparent height now is higher because you are below. But if you are above and you look at the coin will appear to be shallower, right? So that's just a question of the point of view. When the question is asking for someone who is under the water, then the thing that you now look for is the light ray that come from the thing that you saw. And the light ray the thing that you saw, the light ray came from up here and then get bent closer to the normal. All right. So you have now this apparent height, apparent depth, but they are the same Snell's law. And now this is another very easy example of what is Snell's law that gives you a displacement. And when you are in a hallway, and let's say Empire State is outside, and you are working in the area of 34th Street, but when you walk through the hallway, depending on the thickness of the pane of window, if the architect were to have given you a little bit of something to make you not so monotonous, what they would do is to have this section of the hall with the window pane thicker than this other section, so that as you walk along, you'll find that the image of the Empire State seems to flicker. You know, when I'm walking over here, it's over there. But then when I come over here, it seems to be shifted a little. Then when I walk some more, it shifted back. That would break the monotony. And for you, you can just say, gee, I can understand it very well. When I have any kind of slab of material, the image of what was originally here, now instead of coming straight through, because of Snell's law, is now displaced sideways. All right, I mean, that trigonometry is so trivial. All right, so these are all, but now comes a very important principle. It's a very important principle for you in the medical profession, because it is based upon this that you have what we call fiber optics. Well, it all comes from Snell's law. You say, if I have something which, it supplies light, and I now shine it up to, let's say I am inside the water, and I am now shining the light through it. According to Snell's law, when it comes out, the refracted ray will be bent away from the normal. Okay, now you say, all right, so if I shine it here at this angle, it will be refracted at 65 degrees, let us say. But now I shine my light torch at a point further away from me. If I shine over here, at some point, the refracted ray will be 90 degrees. But if I shine even further, I shine the torch, my flashlight, over here, then according to Snell's law, it's impossible. I can't have more than 90 degrees. And therefore, Snell's law says, when you exceed 90 degrees, no more refracted ray. It's only internally reflected ray. This is what you call total internal reflection. And this is called the critical angle. And the critical angle is now, we call it theta c for critical. And it is now N2 over N1, where N2 is over here, N1 is over here, because you see I am inside and N2 is outside. And N2 is now less than n1, and this critical angle sine theta is n2 over n1, and using for oh, you can therefore take the water, which is, I forgot now, either it's 1.3 or something, and air is 1. You can then figure out that the critical angle is, what is it, about 49 degrees or something like that. All right. So this is a very important principle, and we will see how or what the application is. And for medical science, without it, the healthcare workers cannot probe inside my what does it call it? They call it endoscopy, and whatever else do they call it now? Through the bottom is something else. Do you know those medical terms? The one to look through inside by inserting a tube all the way in my throat is called what? Gastroscopy or something? Is anybody in the medical profession? Endoscopy. How about the other opposite end? Opposite end is it the same? Colonoscopy. Thank you. You see, I only know they poke here and they poke there, but anyway, and the fact that they are able to poke and then look inside is all because of this Snell's law, total internal reflection. We'll come to that. And now the book also shows you something about how you say the diamond is sparkling. Well, it sparkles because of total internal reflection. Any light that comes in will be totally internally reflected, and this angle of incidence is 28 degrees. So it really is the light that comes in, they will be reflected and come out, reflected and come out, so that you get this extra sparkle instead of like the normal kind of glass. Oh, they will come in and they will go out there. But for diamond, it actually, because of the angle of because of this critical angle is smaller, oh, it actually can reflect more of it out, less of it to come out. And then what they say is, gee, what if I now put this this diamond inside water? Well, the density of water is higher than the density of air, so it changes the critical angle. And when it changes the critical angle, it does not now have the same sparkle. Well, yeah, they show you some calculations. We don't need to work on the calculations here. The sparkle of a diamond, and so it's not important. But for glass to air, oh, there are people who make use of that. Now this is what I was referring to. The reason why this total internal reflection is so very important and useful, advancing the whole career of healthcare, is that they are able to find a material that's called a fiber. Of course, the engineers, they had to spend a lot of effort in looking for the right kind of fiber, because can you imagine, they stick it into my colonoscopy, but the fiber is toxic. Would I want them to insert that kind of thing inside my body? I would say no, thank you, please, please, right? So they cannot just simply use any kind of material. They have to, I guess, test it out, and then they have to wrap it around. They call it cladding. I guess it's like cloth. I'm clad in this cloth, right? So this fiber is clothed with some material which has its index of refraction. All right. So they call this the core, they call this the cladding. And what they now do is they say, gee, I send light in, because what I do is this is the tube that has been inserted into my throat or to my bottom. And now I'm looking for tumors. I'm looking for whatever funny things there are in my system, in my body. And the light that comes from this tumor, now when it enters the tube, it will now be totally internally reflected. And when it is totally internally reflected, it will then come over here. And when it hits here, this angle is also greater than the critical angle. So it would then be reflected. And when it hits here, it will still be greater than the critical angle. So it will be reflected, and it will be reflected, it will be reflected. And you see that it has turned, it has bent. And this total internal reflection continues to work, operate, even when this tube is bent through my throat into my wherever my chest and so on. So it actually enables the surgeon, the is the ENT, I guess those are the ear, nose, and throat. Is that the whoever are the doctors, surgeons? They would actually be able to look at my colon, right? Because my colon is curled around all over. So this is the basic principle. And they now will have, well, they then will be able to say, yeah, I am able to have a certain cone of observation. If anything is within this cone of observation, it will come in and it will be totally internally reflected. Anything that's outside of this cone of thing would not be totally internally reflected. So only certain angle. All right. So you can see how total internal reflection has a big application. And the actual angle of critical angle depends on the index of refraction of the the cladding, the covering, compared with the index of refraction of the actual fiber, the actual core itself. And the engineers, they have already figured out, they measured whatever is N1, whatever is N2, and they know what is the critical angle. Now, another application of this Snell's law. Any questions at this point? Okay. Another application of this Snell's law is a very important example. It's an important example for people traveling in the desert, or not quite desert, but in, let's say, even if you're somewhere in Arizona and out in the plains, it can get very hot. And when the air is hot, the sun is shining on the ground. The sun is shining on the ground, so the air becomes hot. But we all know hot air is less dense. Hot air density is less than cool air. And therefore, the index of refraction of a hot air is less than the index of refraction of cool air. Well, this sand or this road can be like 100 degrees because the sun is beating down on it. So many photons are smacking it. So this one, the actual ground surface could be very, very hot. Whereas up here, it is still, let's say, 85 degrees Fahrenheit. And therefore, there is now the issue of potential of the index of refraction, that the critical angle is reached when you're looking at a tree that is very far away. The image of the tree, the light ray from the tree, it would now be bent further and further away. But then at some point it cannot be bent more than 90 degrees, so there is total internal reflection. All right? There's total internal reflection. And then what you see is now over here. So this is this total internal reflection. And when you are traveling, whether it's in the desert or on a real plain where there's a lot of hot sand or hot road, then you're likely to find this thing called a mirage. And I just downloaded a very good picture. I downloaded a very good picture because here you are. I don't know where this picture is, some part of Nevada or some part wherever. You are now traveling in a very hot region. When it is very, very hot, you suddenly see, hey, in front of me, there is a sort of a patch of blue, right? You would then say it is what? An oasis, right? You would say, gee, I see now in front of me. Yeah, one of the past classes, I already mentioned that, but I downloaded this picture because this is more dramatic than the other sort of like a child's picture, right? Cartoon. This is actually not a cartoon. This one is a real picture. It's not a cartoon. And it actually does show if you were, driving somewhere or you were on a camel, and you really are very hot and thirsty and you are saying, ooh, now I see water, right? Now I see water. Isn't it nice blue water? And there are whatever looks like this in the oasis. So you go some more. But the closer you are, it is still that way. This is what they call a mirage. Why? Because this blue is a reflection of the blue sky. This blue is a reflection of the blue sky. It is not that there is water. So total internal reflection is an important physical phenomenon in our daily life. Although you say, I will never be on a camel, I will not be, going on a desert, but there will be times when you'll be driving and you will meet this. Okay, now another aspect of this, I like to also quote this, is you are diving, scuba diving. If you're scuba diving, you'll be underwater. When you're underwater, you can look up, but anything within 49 degrees, you will see the atmosphere or the sky that is above you, because the critical angle is 49 degrees. So anything within that cone, you see your friend standing on this side of the lake and you see the palm tree on that side. So when you look up within this cone, you see the contour of your lake. But anything outside of this, you're not seeing the sky, you're not seeing anything, you're seeing the bottom of the lake. And the warning for scuba divers is that when you are going on a scuba diving, you are going long distance and you have a tank, and the tank is enable you to go for, let's say, an hour or an hour and a half. You better watch it because you are now going and going and going. You keep looking and then you seem to see blue down here. But what is blue down here is really over there. The sun is shining on the sea, right? And so things are good. But meanwhile, above you, the part that is really important to you is that your boat, there may be a thunderstorm or there may be a very heavy cloud. So you have to be aware that what you see ahead of you is not always what looks like what is above you. You know what I'm trying to say? over here, within this cone, what you see above you is indeed what is above you. But when you see outside this cone, what you see is not what is above you, but what is ahead beneath you. All right. Only if you are a scuba diver, then you will appreciate. I'm not a scuba diver, but I'm aware of the physics issues involved. Okay. And already we have fiber optics, and we have this. Okay. So now next we come to prism. And the law of prism is one which actually is relevant to rainbows, because what we have so far been talking about is index of refraction for Snell's law. But when the people started looking more and more into Snell's law, and one person that was the one who did a lot at the very beginning is Sir Isaac Newton. After he had already sort of settled and became famous for gravitational, mechanics, for the Newton's gravitational law of universal gravitation, well, then he turned his attention to light. And he was actually thinking of the corpuscular theory of light, but he did not have quantum. So his was not yet the photon, but he was trying to, but he did not really succeed. But what he did sort of look at was that there is a apparently rainbow of colors that comes when you shine white light. When you shine white light on any prism, what comes out is a range of color: red, orange, yellow, green, indigo, violet. What you get out on the other side is a rainbow. And indeed, today we have many such examples, all right? And why is that? Well, that's because the index of refraction depends on the color. The index of refraction depends on the color. And so the engineers, the scientists, they have actually measured, and they have a table for it somewhere. Yeah, they have a table for it, and they say, oh, I have measured the index of refraction for red light. It is 1.52. For blue light is 1.53. And you can see that the index of refraction is bigger for towards the blue end, whereas for red light, the index of refraction is the smallest. All right. So this is what you call Roy gives, the way I remember it. Red, orange, yellow, green, and then indigo and violet. So Roy give. Whereas other people would like to remember it as Vitgyo. V, violet, indigo, blue, green, white, orange, yellow, orange, red. So you either remember it as Vitgyo or Roy give. But anyway, you say, I don't care. Yes, Roy G. Biv, but I remember it's Roy Give or Vitgyo, Roy Give. Yeah. All right. So, but the important thing is that now we recognize that the index of refraction depends on the color. Okay. And oh, this is just a sort of a thought thing. Can you indeed have the prism that would now bend the light upward? It all depends what is the index of refraction of the surrounding to this glass. So, and indeed, they say, could it even be possible that I have this prism in this medium where the light isn't bent at all? Well, that's very easy. If this index if this prism is in a medium which has exactly the same index of refraction, then there is no refraction. It just goes straight through because n1 equal to n2. Therefore, theta 1 equal to theta 2. But this is just sort of a thought, kind of like Gedanken experiment. You're not going to be able to find a glass prism inside a medium which is not glass but still has the same index of refraction as glass. So it's just we will go. I want to now come to my favorite. We see rainbow. Did we cover rainbow already? We must have, right? I must have asked that question before. Yeah, okay, all right. So then it's then we don't need to spend that much time except to remember that rainbow is because there are these water droplets, and these water droplets made of water has an index of refraction of I forget, is it 1.3 or something like that? And when you have sunlight that comes from the sun, it will now be bent towards the normal. Yeah, 1.33, thank you. So it will be bent towards the normal, and then when it comes to this side, it will now be totally internally reflected because it is, what is it, 49 degrees is the critical angle, and therefore it will now be totally internally reflected, and then when it comes out, it will be bent away from the normal. And because violet, the blue end, is index of refraction is higher, it will be bent more away, whereas red light is bent less. So here now when it comes, it will be bent away from the normal less than this. And when you are now on the ground, you will now see red light because it was bent less, but you will see violet light or blue light at a more horizontal angle. So that's why you see Roy give red, orange, yellow, green, indigo, violet. So that's how you get the rain colors, right? But the important thing is that you must have enough water vapor to be able to see that. And there is the primary rainbow. We have seen it already, and it is the experts tell you that you should look up around 40 degrees from the horizon in order to see the primary rainbow. And the primary rainbow, oh, somebody had a question? Is that what the sound is?
Yeah, Professor, can
Yeah.
you hear me?
Yes. Yeah.
In accordance to this reference sunlight,
Yeah.
like where it is dashed, this is in reference to the like sunlight coming at that angle. We're looking away from the sun, right?
That's right.
But
That's right.
but
Yes.
my question is, if the sun was set much lower, at a lower than 40 or 42-degree angle, and we're looking
Yeah.
away from the sun, but there's still heavy rain, in theory, wouldn't it not make the primary rainbow? Now it would make a different color. It would just be a red rainbow, if I'm not mistaken. The color would change, correct?
Yeah. Well, now that gets a little. I need a engineer to work out what you're talking about. What you're saying is the sun is not. Let's say this is my horizon, right? And the sun is not at this angle, but is now lower. So it is now shining on this water vapor at a different angle. What is the kind of rainbow I see? I have not seen a situation where it is not the primary rainbow that you see, but it is a secondary rainbow. That's what you're asking.
Sort of, not the secondary rainbow, but a rainbow of a different color where the wavelength of blue would not be seen. You would only see red because of the angle.
No, 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 no. You will see a range of because the there will be many different water vapors. No matter which way the sun is shining, there will be many, many. And so you will be able to see the red and the orange and the yellow and so on. But the question is whether what you see is primary, is sort of like a little bit low now, and what you now see mostly is the secondary. That's what you are saying. And it could happen depending on the situation as far as the moisture is concerned. It depends on how. The other thing about the intensity of this rainbow is the density of your water vapor. You know what I'm saying, right? For me to be able to say, oh, there's such a lot of red and violet and so on, that's because I have many of these, gazillion number of these water vapors. But if, let's say, I don't have that many down here, but I have a lot more up there, then I may see a little bit stronger the secondary rainbow than the primary. I mean, it's an interesting question which the weatherman, they can help you. Or maybe not the weatherman, but the engineers behind the weatherman. All right. Yeah, I mean, this is a picture involving now the same sunlight, but now higher up, it involves now double. And when you now see it, it will now be inverted. I mean, these are things that, you can bring your siblings along and then say, whoa. And I always tell my architect students that when they design a new, hotel atrium, that they should have a fountain in the atrium. And then with the fountain, you have water vapor, and then have the light shining at the correct angle so that all the kids coming by this fountain, oh, they can see a rainbow, because that gives a good sense of, a nice atmosphere, right? So this is the kind of thing that we need to be aware of, even though we may be very concerned about the Omicron, we're concerned about this and that, but it would be good to have this in front of us as we walk. Yeah, and so now what you were asking, you see a very intense red, and there's still some blue, but it's sort of like not as intense. That's what you are asking for, right? This is the setting sun, so it is not as clear. But because it is a setting sun, the secondary rainbow now is more of it I can see. And that is indeed a secondary rainbow with the red on the bottom and the violet on the top. All right. Any comments or questions? Yes. No. Okay. All right. So now we also need lenses. Now we have covered the lens formula. I just want to just quickly mention that in the biomedical profession, you do use lenses all the time. So at least we should be aware that there is this thing called converging lens, and there's this thing called diverging lens. And we have this terminology of what is the focal length, what is the curvature, the center of the curvature of the lens, and we have this object distance, image distance. I think we have it somewhere, right? Diverging lens, and it seems to come from this point, which call this the focal length. We have these parallel rays called the principal axis paraxial rays, and when they come through the diverging lens, they would then appear to come from this focal point, and this is what's the F is the focal length, and We have converging lens, focal length, ray diagrams. Well, I won't spend that much time because you already have it in your notes, so you know. But the main thing is that there is this formula. Where is it? Where's the formula? Come on. Yeah, you know about this because without this, you will not be able to examine things that you need to look for, right? Yeah, that you have this convention that says that if I have a lens and I have something that is at a certain object, DO, that's the object distance, and is to the left of the lens, then it is positive, and the focal length is F, and this object is placed here, then if the image is over there, then this is DI, the image distance. And when the image is to this side, it is now positive algebraically. But if the image is inverted, it's negative. And the magnification is HI over H0. So it is now, according to this formula, minus DI over D0. But because this DI is negative, oh, yeah. Oh no, excuse me. For a converging lens, this is the I get confused myself. This is positive by the convention, so that a HI is now inverted and it is negative. If it is inverted, it's negative, and this DI is positive because it's on this side. D0 is positive when it's on this side. When the image is on this side, it becomes negative. Anyway, you just refer to this convention, okay? You refer to this convention. We don't need to work this out. Now, we need to come to chapter 27, which is the interference. And we need to learn about, well, of course, if they interfere, if the path length is half a wavelength, they will interfere destructively. If the difference in path length is an integral multiple of the wavelength, they will interfere constructively. And we now have this well, we have gone through this, so it's just, and you now come to a on the subject of double slit experiment called the Young's experiment, and it is something which can help the scientists to figure out actually the wavelength of light, because sometimes I don't quite know what wavelength I have. And you can then use this to now, by looking at the fringes, measuring it, you then say, oh, this light is this particular wavelength. All right. And the way you do that is you now say, I have, because I know my, it's like this CSI, crime scene investigation. How do you know this is the rifle that was used in whatever was the crime? Well, what they do is they know that with that rifle, all the bullets of the same caliber, when you fire, they will always have the same velocity coming out of that rifle. And how do they figure it out? They just simply take that rifle and then in the lab, they shoot it at the block. Hanging pendulum, if you remember your 203, a hanging pendulum, a block. and then the bullet will go into this block, and then it will recoil, and then it will rise, and you can now figure out from the height it rises, oh, what is this velocity of this bullet that came from this rifle? Well, likewise, if there was some particular kind of light ray that is so mysterious and you have no idea, one way to do is to use this double slit experiment, because you know what is your your width of this double slit, and you can measure the images, the fringes over here, and you now if you measure the fringe over here and you know the angle, you can therefore say, yes, I now know what is the wavelength, because if I know this angle and I know this the width, I have figured it out. I have measured it rather. All right. Did you kind of now see the relevance of why would we even want to know this thing called Young's experiment, apart from being a famous, Young, but it is because it is a good calibrator, good way to calibrate what is the unknown wavelength. Because you can say, gee, I can tell it's sort of reddish, I can tell sort of it is orange, but I cannot say it is exactly orange, it is exactly red, because our eye retina, it just is sensitive to red, green, and yellow, and other mixtures of it would then give a perception of indigo. Other mixtures of it may give a sort of a indication of orange. But if you really want to know more precisely, that's what you use. All right, and we have done that, and we have done the the, the double slit experiment, and we can remember the basic formula for bright fringes and for dark fringes, and you know where to look. If there's any question involving fringes, just where to look, right? And what to use, and you know what the angle mean. Okay. And this is Young's double slit experiment. I'm sort of reproducing the slides that we have earlier from earlier lectures. Yeah. And here, the central fringe is white because my light that came in was white. So this is white fringe. But now these seem to be red fringe, green fringe, and so on. But that's because for different wavelength, the fringes occur at different places. And so I can therefore now tell, oh, this is now the orange. No, this is not orange. I don't know. Reddish fringe. And it is because the wavelength of near the red end. And oh, by the way, you will notice that I from 27.2 I went to 27.5. I don't know. Does anybody know what's the meaning of 27.2 versus 27.5? People are not paying attention. I hold on. My friend is looking up his lecture notes. Yes. I am letting you off. What am I letting you off? The thin film interference. Yeah. Which you already had in test 3 anyway. I'm leaving it off for your final. I'm also leaving off, what's the other one? The air wedge. Yes. Because you're not going to be involved as a biomedical profession in those things. So air wedge, yeah, where you have the air between this material here, a thin film here, you know, right? Yeah. So anyway, I have decided, yeah, aren't you glad? You get a little more relief, right? You can now, no, reflection of mirror, it should not be one where you say, oh, what is the angle of incidence and reflection? If you don't know about a mirror, I think you should know about the mirror. After all, you use the mirror every day, don't you? Even if you are not going to work, don't you look at the mirror? So you should know about the mirror. But thin film interference, yeah, I will. Oh, you only use the mirror sometimes. Thank you. You're not going to spend the whole day in front of the mirror, right? And say, hey, mirror, mirror on the wall, who is the fairest of them all? Well, no, I'm not the fairest of them all. I'll throw this mirror away. But anyway, for diffraction, we should know that there's this Professor Huygens who says that the wavefront, each one is a source of a spherical wave. We just know the principle. We don't need to know the actual mathematics. And this is just to, I mean, we have seen it already. It's not such a very it's a it's an important idea, all right, for what is a wavefront. Huygens principle, we already learned that. And you have light coming through a single slit, it will now have fringes because of diffraction. Well, we have, this is really basically the same principle as the Young's experiment, except that now this slit is now by itself. And you now look for the fringes. Destructive interference. It's the same equations. And we will not do this, although you will find it in your and we end with Christian Huygens, but you are not going to be asked when was he born, what did he do. These are just for your own enjoyment. But I will now end. Oh, I'm early, but anyway, I will end by reminding you that it is 2 days time on Wednesday, and it will be exactly 6 o'clock to 8:15, but you better sign in 10 minutes earlier. There will be a proctor who will be there, who will sign you in, and you better be at Baskerville room 210. Rain, snow, or shine. Oh no, there won't be any shine because by 6 o'clock there's no rainbow, no sunlight. But anyway, you have to be in Baskerville room 210. I don't know where it is. I've never been to Baskerville inside. Sign in 10 minutes earlier, and the exam will appear at 6 o'clock, and it will go until 8:15 p.m. All right. There will be questions from chapters 28 and chapter 29. After all, photons play a very important role. And, when you have photons knocking this electron out, it loses something, I don't know what. Maybe the photon gets a little dizzy when it knocks against the electron. I have no idea. Professor Einstein knows, right? But you need to know because it's an important information about photon, about photoelectric effect, and so on. So you need to know chapter 28 and chapter 29 because we were on it most for the past 3 weeks or more, right? Since test 3, we have all been on chapters 28 and 29. So 28, 29 will be on the exam. But now, what was it? Sound and is that chapter 16, 17? Yeah. I will not say, you better know all about, 16 is not on, and what is it, 17 is not on. And then what is 18 now? 18 is Coulomb's law, right? So you will not be asked for Doppler effect. And also for chapter 28, you will not be asked for the relative velocity, relativistic addition of relative velocities. Yeah. So 16, 17, no, 18 is what? 18 is Coulomb's law, right? I get my numbers all that mixed up. Can somebody help? Yeah. So Coulomb's law is certainly on. Yeah, right. Coulomb's law is certainly on. So 16 and 17, bye-bye, don't worry. And then for the rest, Coulomb's law and so on, we have already, Gauss law, we have already reviewed it in our review of chapter 18 and so on. So you look at those. But anything where I already put for engineers, you can say, I don't have to worry. All right. Anything where I say it is for engineers, you can just forget. Okay. And we won't have chapter 23. Oh, okay. All right. Now I'm going over my 18, 19 are in the lecture notes on chapter 18. 18, 19, they are in the same. When I had the PowerPoint, it included 19. Yes. And then 20, yes, you need to know about the resistance, the electric power, resistivity, Ohm's law. Now, you must know. And you know about the parallel, when you have the lights resistors in series or in parallel, you should know. Even for practical purposes, you better know. And for magnetic fields, 21, you should certainly know. 22, we have learned about the Faraday's law, you better know. Lenz's law, you better know, right? So magnetic flux, Gauss law, electric flux, you need to at least know what it means and then be able to use it. But chapter 23, I will not have. And for 24, 25, we already went over 26, but we won't deal with lenses in combination, human eye, angular magnification, compound microscope, telescope, lens aberrations. No. I will not insist, because if you ask me questions about the human eye, I only know my own myopia, but I cannot help anybody else, right? And as I said, for chapter 27, no thin film interference, no Michelson interferometer, no resolving power, diffraction grating, compact disc, X-ray diffraction. Okay, have I already sort of, yeah? You now know roughly, and now, as I keep reminding everybody, you are now given at least 6 minutes, so you have time. And the main thing is, always take time to read the question, because the wording sometimes requires you. No, not 27 questions. Now I have just said, if you didn't join, do we have a punishment for people who didn't join in time? And say, because you didn't join in time, you will be given 27 questions, while the rest of us who were here earlier, we have only to worry about 22 questions. I know you were 5 minutes late, but anyway. And for 28 and 29, you better go over it, because we spent quite a bit time on Professor Albert Einstein. And also on de Broglie, yes, de Broglie, yes. All right. Let me see what else I have. Oh, yes. So I don't know what's your plan for, your career, but whatever career you have, be good in thinking outside the box. I would like to encourage everyone to think outside the box because whatever the circumstances, you may be part of a healthcare team in the hospital or in some medical. Somebody had a question. What? Say that again. What was the question?
Professor,
Yeah.
can you hear me?
Yeah.
Okay, can you make sure when you attach like pictures or images that we don't have to go to a different page because it wastes a lot of time.
Yeah. I don't know how to do that. The only way I do that is to, it says, insert a picture in the mesh box, Dropbox. I don't know any other way. I wish there were. I agree with you. It's very annoying because you click to a different, window, and then it takes a while for it to clear up. It sort of blocks part of the picture. I know I myself have tried it as a, preview, right? And I don't quite like it, but I don't know of another way to do the pictures. Was there another question? The TA, he will not be able to address. I will be on chat. I will be there from 6 to 8:15, and if there are happens to be technical issues or something, I will be able to chat. You chat with me, and then I will answer when I look into it and say, oh yes, such and such. But when you ask a question, you better say the context, because I wouldn't know when you just say, hey, question number 7, what do you mean by such and such? I wouldn't know what is question number 7. You will have to say, oh, on this young slit, double slit experiment, you had this issue or question with such and such. Then I will know when I look up my own notes which question you're talking about. All right. So when you chat, you be specific of the context of your question. Yeah, I. The other thing is, you better allow your browser to have pop-ups. I know. I hope you know what is pop-up. You better make sure that your browser allows for pop-ups, because that's what Blackboard says. You need to be able to put it onto a new window. Uh, no, no, no. Well, I don't know about that. The the TA is supposed to send me the lab grades. So whatever late report, you better send before then. The TA, the department has already sent an announcement to all the TAs that they have to send the lab grades in to the teacher, to the instructor, by Friday evening. So you better have whatever late lab reports, send it to the TA before that. Okay? Because otherwise he will just simply say 0 for lab 3, 0 for lab 4. And then you come to me and complain, and I say, well, I have to rely on what he tells me. Uh, when you send in the lab report, the TA is supposed to acknowledge it or what? I don't know the procedure between you and the lab TA. I think there's a session today. I don't know if there's a lab today. Well, you can send an email to this TA and say, did you receive it? But yeah, email your TA again, because the other thing, I'm sorry for making all this. In your career, you will meet similar situations, but you have to be persistent without being nasty, but you have to be persistent, right? In whatever career, whether you are in the healthcare career or whether you are in the medical research career, there will always be a corporate context. There's always issue of, gee, somebody is not taking care of me or stabbing me and so on. You have to be persistent, okay? And am I going to drop the lowest grade? I look at your R ratio. I will not say anything beyond that. But it will take a bit of work on my part to decide on the grade. And I am not one to now say, you're fired. I'm not one to say, you don't deserve. But if you indeed are really doing not that well, such that you cannot imagine that you will have that extra, hour, then I think there's still time to withdraw and then take the course again. I think today is the last day, something like that. You still have time to withdraw. And I will tell you that there was one class, 203, maybe 2 or 3 years ago, when somebody was not doing well. And then I said, well, if you don't have that confidence, you withdraw, take it again the next semester. And he did take it again next semester. He got A, because he already sort of heard it before, understood it, and then the second time around, he aced it. So do not be totally discouraged just because you're not doing well, and you didn't do well for test 1, didn't do well for test 2, didn't do well for test 3, and it doesn't look like you'll be able to have that kind of a R ratio. Well, then you still have time. But I'm not basically saying, you'll never have a chance. It's rather that it's your own decision, but you can have, actually, if it does not affect your financial assistance and all that jazz, all that issues. Any other comments or questions? Yes, persistence, or another word for it is perseverance. But do not be nasty. There's a difference between persistence, nastily persistent, and versus something which is persevering but still being nice, right? Because you don't want to create enemies more than you already have. And what you want is to sort of be nice even to your enemies, so that the enemy will at least not enjoy beating you on the head, because the more you hit back, the more he beats you, and he's the vice president, he's the senior vice president. Oh man, does he not enjoy doing that. But if he can see that you indeed are working very hard, well, maybe, somewhere you just have to keep being, good. Don't lose heart. Okay, now what was the final? Say it again. What was the question now? I didn't catch all of it. Somebody had that question now. Say it out loud.
Will the final be similar to the other exam? I mean, question with the formula first and later with the calculation?
I will have some that will be that way, where it is multiple answer with formulas that try to confuse you and with the calculation. But not all questions can be like that because they're too simple. So there are some that I cannot even think of ways of confusing you. So it will be just give me the answer. All right. I mean, I would try to make it such that you have multiple answer and calculator formula, but not all the time. So you will have to see. Uh, I think there will be more multiple answers than calculator formulas. Partly it will be easy on the grader because it will be, all right. So, but I haven't yet. I'm still struggling with how many multiple answers, how many calculator formulas. So, I mean, it would be, I think, from your point of view, great if everything is multiple answer, no calculator formula. Yes, I know. I will try to make it not so difficult, but I tell you, I have been struggling just as hard as you have been. From the opposite side, you see, you're trying hard to be prepared. Me, I'm trying hard to set up this exam in the style of Blackboard. It's not like the way I used to set up the exam. It was much easier. Now it is in the style and the silliness of Blackboard, and I have to live with the silliness of Blackboard. Yes, you can help me. Yes, thank you. I can hire you as my aide, right? And then you will know what exactly questions to ask. I don't know how to do that, and I am not that happy with Wiley Plus myself. I don't know how to do. Yeah, some other professors they use Wiley Plus, right? Any other questions? Well, this is the time to ask. Okay, so we will now end the session. And as I remind everybody, please be at Baskerville 210. Yes, have a great winter break. But before the winter break, I have to go through all of the grade, the course letter grading and so on. So, all right, I hope that you can have your final grade certainly before December 4th, 25th or something, right? It should be maybe by December, I don't know, 20th. Well, we'll see. I mean, when it gets to be, December 24th, 25th, my children, my grandchildren are coming. It will be a mess in my house here. So I'm not sure I can actually have your final grade before December 24th, but certainly by the Monday after that, which is what, December 27th, I think. Okay? Because it does take a while for me to get all the things together with the. Okay. All right. So I think we have had enough of sharing and have a good rest before the exam, and then after the exam, go celebrate somewhere. Okay? All right. So, yes. How do I curve? Well, that's where I have to spend a lot of time. First, I have to decide the class average. whether it's a C plus or B minus. And then I have to then decide what is A, what's B relative to that. But if you have been getting, so good that it is close to the top, then don't worry, you get an A or A plus. But it is those who now get a B minus. Maybe if your R ratio is good, you get a B. Or those who are already by the regular curve, it's a B, you may get a B plus anyway. So we'll see. Okay. There's still hope. Yes, there's still hope. Okay. All right. Have a good career. And if you need letter of recommendation, well, I don't know. Well, maybe I shouldn't say all of you come to me for letter of recommendation. Because I am not saying that I will now write beautiful letter of recommendation for everybody and say you are the very best I've ever met in my whole life. I don't give that kind of letter recommendation. Yes. Okay. All right. So.
Professor?
Yes.
Will you be teaching next semester?
I won't be teaching this one. I'll be teaching architects.
Okay. I was just curious, in order to gain that recommendation letter, if there was an extra like teaching, well, I know that you're teaching for architects now, but I was wondering if there was a TA or an extra research position we could apply to gain that recommendation letter
Oh,
in
no,
the
no.
future.
Yeah, in the future. My recommendation advice to you is, depending on how the pandemic works out, right? Always have a good office hour relationship if it is live, to have a good office hour relationship. Because letter recommendation, the one who is writing will say, yes, I know so and so. Oh, he shows this character and that character. So you need to have more interaction with the professor, right? For this pandemic, unfortunately, we cannot have live office hours. So all I know is the kind of chat we have in the class, on online. But I will be able to say, yes, this lab reports show that so and so has worked very well, and then he has or she has done well with all of the tests. And so all I can say is that the student or this person shows potential to be a good, responsible such and such. And what I will say in the letter recommendation is that this course included these basic principles that are important for biomedical. It's important for, let's say, if you are into prosthetics, it's important for prosthetics and so on. Because the people who are reading those letter recommendations, they really look for what is your strength, you as the applicant for the particular position. What's your strength? And if you have a resume, you send the resume to the advisor, then the advisor can look at the resume and then say, oh yes, I can see that this so and so has actually been involved with community work, helping even when he is not yet a professional in healthcare, already helping people. Well, those are all things that add to the your application. But maybe I'm really spending too much time on recommending when I don't know yet what the issue is.
Hi, Professor Chang. This is Stanley.
Yes.
Where is Baskerville 210? Is there only one location, and is that on campus?
Yes, it's on campus. Now, as to where, it is in the courtyard. Now, which building it is, I don't know. You have to look in the City College map, you will find Baskerville. You better know where it is,
Yes, got it. Just making sure. Thank you.
I know. Don't walk into Marshak room and say, where is everybody? Yeah, I have not been to Baskerville, but they assigned us Baskerville. So, oh, is that where the high school is? No, I don't know. You better check it yourself. Don't believe whoever tells you, right? You better check it yourself. Yeah. Yeah, you better check it yourself. Where's Baskerville? Room 210. Okay. Any other questions? Okay, I will stop the recording.